Welcome back. This is a Kapitza Pendulum. It's a super interesting system because it wants to stay in the vertical position. In today's video, we will learn how to model, simulate, and animate the Kapitza Pendulum using Python. Now let's get started. First, we'll model the Kapitza Pendulum as a pendulum with length L and mass m. We're going to assume that the rod is massless. Then we'll define theta as the clockwise displacement from the vertical axis measured in radians. And finally, we're going to oscillate the pendulum up and down in the y-axis by this a sine omega t. So then the x-coordinate of the mass is going to be L sine theta, and the y-coordinate is going to be L cosine theta plus this a sine omega t. Now let's do the math. We know that x can be modeled as L sine theta, and y is simply L cosine theta plus this a sine omega t term. Then the kinetic energy is just 1/2 mv squared, and because we only have one mass particle in this whole system, we can just write v squared as x dot squared plus y dot squared, where x is this and y is that. Perfect. Now let's solve for the potential energy. V is just mgy, and of course y, we have an expression for that, so we can just plug that guy in. Then we'll write down the Lagrangian as just a difference in the kinetic and the potential energies. And then finally, we'll plug it into the Euler-Lagrange equation. So this would correctly model the system if there was no friction involved. But what if we want a little bit of friction? We can actually add that in with this b theta dot term. And so this will add a little bit of friction, which is proportional to the speed at which theta is changing. So then we can put a box around this, and then we can go ahead and use Python to solve. So now let's do that. Okay, so I just opened up VS Code and I created a new Jupyter Notebook file. And then I'm going to go ahead and do my import statements, and we'll just run that real quick. Perfect. Now let's go ahead and define our symbolic variables. So we have m, g, l, a, omega, b, and t. Then we'll go ahead and import our dynamic variables. Just as a reminder, dynamic symbols, they have an implicit dependence on time. So this is theta, which is a function of time. Now we can go ahead and define the x and the y position of the pendulum. Then we can go ahead and take some time derivatives. This will just make our life easier in the future. Okay, now let's go ahead and define our kinetic and potential energies as well as the Lagrangian. Then we can go ahead and solve the Euler-Lagrange equations. So I have two different equations here. One of them has damping. The other one has no damping, so if you want to play with this yourself, just go to my GitHub page, link in the description below. You can go ahead and actually run this without damping. So we'll do that, and then after we solve, I'm going to display this in state space format. That's super easy. I'll just copy and paste this guy in here. And so now, when I run this, if everything goes to plan, we should get this nice output right here. So I'll zoom in so you guys can see it, but this is the state space format for the closed loop Kapitza Pendulum system. Perfect. Now, one more quick thing, this is going to be useful in the next file, is I'm going to paste this guy in here. This will just print out the state space format, but instead of this nice fancy print, we're going to actually print it out in ASCII characters so we can copy and paste. So now that we have that, I'm going to create a new file and we'll get started with the animation. Once again, I went ahead and I added a new Jupyter Notebook file, and then we'll get started with some basic import statements. Now let's define the simulation parameters. We have our mass, we have the L, and then we have our damping coefficient right there. You can go ahead and play with these on your own if you'd like. We'll define our initial conditions for the simulation to be theta equals 0.1 radians and theta dot to be 0 radians per second. You can change those as well. I'm just going to go ahead and copy and paste these ODE functions, and then I'll walk you through them. So this first one is the ODE for the system with zero damping. The second one has damping, so it has the friction term. And you might recognize this. I was able to copy and paste this from the previous file right here. So I just went ahead and copy pasted this guy in there. The only thing I had to change was I had to add numpy dot for the sine and the cosine terms. So you see that right there. We have this and that guy. Okay, so now that we have the ODEs, we can solve it very easily. So I'm going to paste this in here. I also have without damping, and then I have with damping right here. So you can just solve the ODE right there, and now we'll go ahead, grab the output and plot the results. So I'll paste that in here. So you see that theta is going to be our solution dot y, and we'll just grab the first one. The second term, if I put a 1 in here, this would now be theta dot. So we'll grab theta, and then we'll just go ahead and use matplotlib to plot that. So let's run that, and there we go. So you see how 0 right here, this represents the pendulum in the vertical position. And you see how we're going to start to the right, and then we're going to go to the left, and then to the right, and then the left. And because of this friction term, we see how we're asymptotically getting closer and closer and closer to the upright position. And then you can see the effect from the 40 Hertz oscillations that we're doing when we're driving the pendulum up and down. Awesome. So this is how you simulate. Now let's go ahead and really do the animation. So I'm going to have some more things to import right now. So we're going to import NumPy, we're going to import matplotlib, and then also this lines 2D that will allow us to do some animations. Now let's go ahead and we'll create a new figure, and we'll set the X limits and we'll set the Y limits. And then we'll just start by having theta be, let's say, 0.2, and time to be 0, and of course A from a simulation it's just 0.1. So I'm going to go ahead and draw in the mass position. So we have the mass X, the mass Y, and then I'm going to draw a circle located at PXPY. It's going to have a radius of 0.1, and we're going to make it blue, and we're going to draw it on top. Then we also have this little pivot. This is going to represent where the pendulum is pivoting from, and this guy is moving up and down. We'll go ahead and we'll draw in the stick finally. So we'll draw a stick from, basically, this is basically the pivot right here, from the pivot point to there, and then the X coordinate is going to go from 0 to PX. So we'll go ahead and run that, and you see we have this beautiful little drawing right here. And so we can even go ahead, if you want, we can update the time to be 1 second, run that again, and you see now, well, 1 second was a bad example. Let's go 001, and you can see how we've moved slightly up. So if we keep advancing this, you can see us moving the pendulum up a little bit at a time. So if I go here, it's even higher. So perfect. Okay, now let's go ahead and actually do the animation. So this code right here, this just draws the pendulum at the particular state that theta is 0.2, or time is what it is, and of course A is just a constant. So now let's go ahead and actually animate this and create a GIF file. So I'm going to go ahead and do another import statement. We're going to import this matplotlib animation. Then we're going to grab the output of the solver again, theta and t. We'll go ahead and create a new figure. We'll set the title. Then we'll go ahead and we'll add some constants. And now we'll do a bunch of drawing. So we're going to create some handles to the circle, the little circle right here. This is going to be the blue circle again. The stick, of course, you know what that is, the pivot point. Then I'm also going to be drawing in a timestamp. You'll see why a little bit later. And then I'm going to add this little playback speed label. And so I'm just going to go ahead and draw in the rest of the code real quick. So this animate function, for each frame, it's going to be in charge of updating the image. And so you're going to see how we're going to update the PX and the PY, and then we're going to move the blue circle to the PXPY position. Then the pivot of the pendulum, we're going to move that to 0, and then this is where the pivot's starting. You see this A sine omega t. Then the stick, we're going to draw it from the pivot to the circle, and then we're also going to draw in our timestamp. So I'll do that, I'll hit run, and this is going to take about 1 minute on my computer, so I'll just meet you guys there in a minute. Okay, that guy just finished up, took 49.1 seconds. We have this nice kind of still image, but if I go ahead and I click on this guy in my file explorer and open that up, you'll see how we have this beautiful GIF file, and this is actually the animation that I showed at the beginning of the video. So one last thing I want to talk about is this playback speed. So we're actually oscillating the pendulum up and down at 40 hertz, but it only appears like it's 2 hertz because we have this 20 times slowdown factor. So I'm going to quickly show you how I did that. So I'm going to go back to this Animate, and I'm going to scroll all the way up to the very first section. And you see I have this right here, this slowdown factor. And so what's really happening is our GIF file, it has 30 frames per second. So when we do the simulations, we want to actually do 30 times 20 or 600 simulation steps. And then when we play it back, we'll just play it back at 30 frames a second. So it will take 20 seconds of the GIF file to create basically 1 second of real time. So that's why the GIF file, it actually will run for 40 seconds. It takes quite a while for this whole animation to run. And the reason we did that is because if we ran it in real time, then this guy would be moving up and down so quickly you couldn't even tell what's happening. So that's why we did the slowdown. So if you guys want, you can go ahead and you can change this guy up. So I could change this if I wanted to. Let's make it maybe a slowdown factor of 5, for example. And all the code is in there, so the frame rate is now going to be 150. Then in the solve IVP, you see how we're still going from 0 to 2 seconds, but now we're going to have 2 times this 5 times 30. So 2 times 5 times 30 is going to be 300 plus 1. So we're going to have 301 frames total. So I'm going to quickly run that guy again. It looks no different here. It should be a little bit lower resolution, but it's kind of hard to tell. And if I go to the bottom and I run this last section again, this should not take as long to run because instead of doing 20 times slower, we're only doing 5 times slower. So hopefully this guy will finish up pretty soon. Perfect, 13 seconds. The playback speed, this is not accurate. I need to actually go in and just change this, but that's easy. If we go back to the GIF file though, you see now it's going up and down very quickly. So this is probably not what you want. This is why I slowed it down to what I did. So anyways, if you found this video helpful, please leave a comment, like, and subscribe. And of course, all the code is in the description. Please just go to my GitHub page. You can start that if you'd like. So sounds good. In the next video, we're going to be looking at another fun nonlinear system. We're going to be looking at the cart pole. It's a very famous problem in control systems. So I hope to see you there.